Computer Science 461, software testing. More verification and validation today. So, again, the two most important words in this segment of the course are verification, did we build the product right, and validation, are we building the right product. So, quick look at what software testing is and how it enables us to perform verification and validation. So software testing is an activity to uncover errors that were made inadvertently as the software was being designed and constructed. People typically don't introduce bugs on purpose. Sometimes it happens, but typically they're inadvertently introduced. And the steps in software testing, that starts in the small, the component or unit level, and progresses to the large, the actual delivered system that you're testing the entirety of. Who does it? Ideally a testing team that's separate from the development team. And for this last question as to who does it, it's good to have developers do the individual unit tests since they're closest to them and can actually write the tests. And some methods such as Agile actually encourage writing the test before you write the code. However, it's good to have a separate team do the integration acceptance testing since developers often have conflict of interest here. They don't want the system to be shown to have any flaws and a lot of times want to be done with it. So if you don't have an independent testing group, it's good to try to take on the view of one when you perform software testing. And also don't view testing as a safety net that's going to catch all the errors that occur because of poor software engineering practices. It won't do that. So it's good to stress quality throughout the development process and then have the testing verified and validate that. So goals of the testing process: one, demonstrate that the system meets the requirements. That's the validation. And discover defects or faults in the software and root out the problems. That's verification. These tests can be a bit more obscure. For example, one is known as the elbow test, which is where you throw your elbow on the keyboard and see what happens to it. Overall, you want to convince system developers and customers that the system is good enough to use or fit for use. So, classic testing model, there are 4 types of tests that go into it. One is unit testing, and this corresponds to the individual unit code modules, functions, or classes. These tests are typically done by the developer since they're closest to them. And then the next step up is integration testing, which tests the integration of multiple components or more than one. And this is often done by an independent test team, although as we discussed before, you can have individual developers doing this. Validation testing assures the software meets functional behavior and performance requirements of the customer. And system testing, this sometimes falls outside the boundary of traditional software engineering and is more into the category of systems engineering, but does the system work with other systems in the organization or with the procedures and processes the organization has in place? So in order to perform testing, you need some types of policies in place, and one of these is important point is exhaustive testing of any non-trivial system is impossible. So you want to create policies basically that says what you will test, how frequently you'll test, and when you're done testing. For example, all functions accessed through menus should be tested at least once. That's a good testing policy to have. And a good question is, when are you done testing? And there are several answers to this. One of them is you're never done testing. It just shifts from the organization that produces software to the customer. The second one is when you run out of time or money for testing, which seems to occur a lot in the industry. And the third is after you reach some statistically defined point. For example, when you're 95% confident that the probability of 1,000 CPU hours of failure-free operation is in a probabilistically defined environment is at least 99.5%. So some keys to successful testing process. One, you want to specify the requirements in a quantifiable and testable manner. And we kind of hit on that in 460, but here's where it's important for 461. So if you did your job with your requirements document and made testable requirements, it's going to make life much easier in 461 now. State your testing objectives. Why are you performing the test? What are you attempting to achieve or show with the tests? Develop user profiles that reflect the actual users and how they will use the system in practice. Develop a test plan that emphasizes rapid cycle testing. and use formal review techniques prior to testing. So again, those walkthroughs and inspections do serve a role and help lessen the amount of testing that you have to perform. They're not just theoretical exercises. So if you're reading Somerville, he kind of goes in the opposite order in terms of talking about the different types of different phases of testing. I prefer to start with the unit component testing, or testing in the small. So unit testing and component testing are generally the same, and the goal here is to expose defects in the individual parts of the system, functions, methods, object classes, and or even composite components made up of several objects or functions. But you want to take those individual units and expose defects in them. So individual functions are obviously the simplest to test, and you can do this with different input parameters, stressing the boundaries. What's the smallest input you can have, what's the typical case, and what's the largest one that you can have. For object classes, you want to design tests to provide coverage of all the features of the objects, and then test their operations in isolation. And then set and interrogate all the attributes, test your getters and setters for an individual class, and then simulate all the events that cause a change of state. So you can use a state model like the one specified by Harrell in 460. And be sure to design tests that execute every error handling path. If you don't, then you may get a failure when that path is invoked, and that might exacerbate an already dicey situation. So interface testing is the next phase up, and components are made up of several interacting objects. You test the interface between the objects rather than testing the individual objects. And so here we're testing how or if the components will actually fit together. And you can use drivers and stubs to do this. So you might recall those terms from CS 151. Drivers are main programs that are designed to stress classes or functions that have been developed. And stubs are simple replacement for classes or functions used to test a already developed main program. So types of interfaces that you'll want to test between objects or between methods. One are parameter interfaces. These are the data passed from one component to another. So when you're done with component 1, when it passes values to component 2, do those pass correctly? Shared memory interfaces, if there's a shared block of memory between two components, do they play nicely? Do they cede control when they're done reading or writing from that? Procedural interfaces, one component has a set of procedures that can be called by the other. Does the first one actually call the other one successfully? And then can you pass messages between individual components to request services and get the right values back? So types of errors that you can get in these interfaces. One is misuse, a calling error. So the person developing object 1 that calls object 2 didn't know what parameters to send in, or send in the parameters out of order. How can you correct that? Interface misunderstanding again goes to misunderstanding the specification of the called component, and timing errors. These can occur in real-time systems. So general guidelines for interface testing: examine the code to be tested and explicitly list each call to an external component. Always test with null pointer parameters. Design tests that cause the components to fail, and use stress testing. For example, give more messages than are likely to occur to see if it will actually break. Twitter actually started doing this because they had trouble because of the large number of people wishing each other Happy New Year in Japan. Would actually cause Twitter to break. So Twitter started doing stress testing where it was getting more tweets than it was designed to handle, and actually handled New Year's in Japan pretty well after that. Design tests that vary the order in which components are activated, and also avoid Big Bang testing. Big Bang testing is a fairly lazy approach of throwing everything together at the last minute and just hoping it works. Causes a lot of problems, and it makes the testing process harder than it should be. For integration testing, it's good instead to plan the order of integration. For example, in extreme programming, the customer often decides what the order of integration is, which are the key stories they want to add in. A general rule of thumb is to integrate the most frequently used parts first, and as a result of your test, you may need to repair, reintegrate, and retest. That's called regression testing. Two approaches to integration that are fairly common. One is top-down integration. Basically, this is an incremental approach. The modules are integrated by moving downward through the control hierarchy. So you start with the main program and then tack on the sub-programs that you need. And you can do this depth first or breadth first depending on the program structure and how you want to proceed. So the main control module is used as the test driver, and then you have stubs for the individual components until you actually develop those components. And one nice thing is you can use regression testing to test the already integrated components after they're introduced. Bottom up begins with the construction and testing of atomic modules. You then combine those little modules into clusters, and then you write a driver to coordinate the test cases. Test the cluster, remove the driver, and further combine clusters, rewrite the driver to test the larger and larger clusters. And you'll also need to perform, when you're doing integration, you'll need to perform something called regression testing. So every time you introduce a new module, the system changes. You get new data paths, new input and output, new control logic, and a lot of times adding things in can break things that used to work. So regression testing helps to ensure that changes don't introduce unintended behavior or additional errors. And you can perform regression testing manually or automatically using capture and playback tools. Basically what you want to do is re-execute a subset of all your test cases or all the test cases you've developed previously. And so a regression test basically suite needs a representative sample of the tests that will exercise all the functions, any additional tests you want to add in, and tests that focus on software components that have been changed. You can also see a term called smoke testing. And smoke testing, or confidence testing, is a preliminary testing to reveal simple failures severe enough to reject a prospective software release. Here you have a subset of test cases that cover the most important functionality. You select those test cases and run them, and you ascertain if crucial functions or the program fail to work. And so smoke testing can actually be run quite frequently and can minimize integration risk and increase the quality of the end product. And it's fairly closely related to regression testing, but it is different. Last but not least, you test the entire system, and this is known as system testing or acceptance testing. And this involves the integration of two or more components that implement the system function or features, and then testing the integration system, the integrated system. So you can do integration testing on an incomplete system, or release testing, which is testing a complete system. And so release testing is the process of testing a release of the system that you're going to distribute to customers. Here you have to demonstrate that the system delivers functionality to the customer, and basically here you have a black box approach where you put the inputs in and you see what the outputs are without looking inside the black box. And you're actually here trying to break the software. So when you do release testing, Whittaker has some guidelines for it. Choose inputs that force the system to generate all the different error messages. Design inputs that cause the input buffers to overflow. Repeat the same input or series of inputs numerous times. Force invalid outputs to be generated. Force computation results to be too large or too small to have overflow errors. Other approaches, scenario testing, you'll remember your use cases from 460. Again, if you did those right, it'll make the testing easier because you have your use cases or user stories. And there was a reason you made these beyond the rate intensive requirement, and that's to do the system testing to see if, hey, does it actually perform all the use cases we said it would. You can also use the sequence diagrams you did in 460 to select the inputs and outputs and to see if the functions calculate things correctly and pass things back to the correct components. Next time we'll get a little bit more into software testing techniques and test case design.